This is the third assignment. In the first part of the third assignment, we had to solve the crossword. We firstly enforce the node consistency. We create a list of words to remove from the variables domain. If the word can fit the given slot, like length, and we remove it, revise. Here it calls AC3, AC3 calls the revise. We check the two neighboring variables. If check if variables overlap, at which point it overlaps. We find the values to remove from X domain. For each value in X variable domain, there should be at least one Y word in the Y variable domain uh, that the letters are same at these indexes. If it doesn't have, we just remove it. And here we remove it. EC3, basically Q, we have Qs, and that stores pairs of neighboring variables. We run through the Q variables. We check for the revise. If X domain is empty, it means that we can solve this crossword. And if it's not, we can solve. Here, assignment completed function, it means it returns true. If assignment is completed, it means all the variable has the values appropriate values consistent returns true if assignment is consistent. If we can put the word into that given variable. We check for all values. All values are distinct, so no duplication. One word can't be placed at the two different variables. We check each variable's constraints. We check can word fit the variable slot by length and check conflicts with neighbors. So basically, at the overlapping index, here's the order domain value. When choosing which value to take, we don't randomly grab the value from the variable domain. We calculate for each value how many options it eliminates from the neighbor's side. So we sort it by eliminated count and take the least affecting neighbors one, and select an unassigned variable to decide which of these empty slots we're gonna be solving. We're gonna use the MRV, minimum remaining value. It means domain size. For that variable, if we're choosing, we have to choose the variable which has the least candidates, and if they are equal, we use most neighbors. Backtrack is the heart of our algorithm. Check if assignment was completed. We select an assigned variable with the least candidates from its domain. We try each value in order. We create that new assignment to basically put that word into a variable. Check if we can put it, and if you can, we save the current domain. For backtracking, we apply inference forward checking here in the future for its neighbors, and we check remove inconsistent values from neighbors domain. We check it. We append here, and if the neighbor's domain becomes empty, we restore domains and try the next value for its neighbor, and recursively try to complete assignment and restore domains if reference was made. Here's the result 679. Here, using these words in the task 2, we had to create a schedule for the given datasets. We import the necessary libraries, load the datasets. I created the dictionaries containing course, student, and course instructor, room and capacity, and also to show the available domains, time slots, and room IDs. Course function is basically it means it has some violation rules for if one student has two exams at the same time, it adds the cost. And here's the instructor conflicts. If one instructor has two exams at the same time, room conflicts. If one room has two exams at the same time, and also room capacity violations, we add some costs. So our optimizer's main problem is to minimize this cost. Get neighbor DF, it takes a data set and pick a random course, change the things. I choose the time slot, It gets a randomly new time slot and changes the previous with new and new room and change the previous room and swap time slots between two random courses. It's not from here picked. This two is changes this picked random course it, but this one it swap time slots between two random course and the simulated annealing. We have current data set schedule and the best data schedule. Here we max iterate through 10,000 and check. We get the neighboring basically new schedule database dataset. We we get the difference if we subtrams here if our new schedule is costs is better, we always set it to neighbor, and if it's not, we use the temperature at the start. Basically uh, it can usually choose the more worst cases because the temperature is high, but by the time goes and at the final stages of our iteration, we will start choosing only the better values. Here's the evaluation schedule for conflicts and printing them. Here's the initial cost was this. I got optimized at this, and it's 5 times better. Here, student conflicts. It was 170. It became 0. Instructor 2 times. This 20 times. But unfortunately, this goes up because I didn't give enough cost weight to this attribute. Here's a optimized dataset. Here's a plot, and I turned it to dataset CSV.